Hey, it's Mr. K doing a video for AP Physics 1 and C, and we're going to talk a little bit about friction. So here is the idea. Friction is going to oppose sliding. I will not say that friction always slows things down because a lot of times friction is going to speed things up. But let's go ahead and talk about what friction is and what we can do. It's a force, first of all. And so if we talk about friction, we're probably going to use units of newtons because it is a force. But there are two types of friction. One is called static friction, and the other type is going to be called kinetic friction. So two types of friction, and there is a definite difference. So static friction, as the name implies, static meaning still, static friction is for objects that are basically still. So if you have an object that is still there, you can apply a force to the object, and if you don't apply enough force, then that object will not budge and friction will hold it in place. But as soon as you apply enough force to it, then it'll start to slide, and that's where we switch over to this other type of friction called kinetic friction. So static friction, again, is the friction that will hold things in place. Kinetic friction is the friction that we'll use whenever things are sliding between two surfaces, and there is a slight difference between these two. So think about, you've got maybe a couch, and the couch is sitting on some carpet. And so here, let's say that this is the couch, and here is that carpet. Well, that carpet, if you've ever tried to move a couch before, that couch is kind of sitting into the carpet, right? So you can lean on the couch, you can push the couch, but that couch is probably not going to just slide unless you really start to put some forces on it. And then all of a sudden it kind of budges, and then it slides a lot easier. It doesn't take as much force to keep it sliding than it would to just unbudge it in the first place. And so static friction is going to be able to scale, because if the couch was just sitting there, and let's say that had a mass MC for M couch, well, here is the force of gravity on it, free body diagram. We've got mcg pointing down, and we have the force normal, which is from the ground, the normal force, and that's pushing straight back up. And really, if there is nobody leaning on this couch, then that's the free body diagram. That's it. Normal force should equal the force of gravity straight down. But as I started to apply a force on it, let's say I applied a force on it to the right. Let's see, here we are. And if I applied a force on it to the right, friction would begin to counter that force to the left. And so if my applied force is to the right, friction would start to get bigger to the left. And, well, the thing's still not going to budge, but if I apply more force to it, let's say it wasn't this long, but let's say it was this long, friction would again try to scale up to match that force that I'm adding to the right. And until you've added enough force where all of a sudden you have so much force that friction just cannot keep up, and in that case this thing will then start to slide, and we would skip from static friction to something called kinetic friction. And at that moment, the amount of frictional force will all of a sudden drop down a little bit. And so here what we need to say is that static friction is a scaling force. It will scale. So it's scaling. Whereas kinetic friction is just constant. It's a constant amount. Whatever the number is we calculate for kinetic friction, it's going to be a constant number. Static friction will be a scaling number because, well, in order to keep something still, there's a range of forces that can be applied to it before it actually starts to move. And so the other thing that would come into play with friction is how much an object is pushing into a surface. So if I'm pushing into a surface and I try to slide my hand along, the more I'm pushing into that surface, the more friction would be there. If you're in band, you try to warm your hands up during a game. It's more effective when you push harder, right? There's more friction there. And so the more normal force you have between two surfaces, the more friction you could potentially have. And so the force of friction, as a general equation, is normal force times something that we call mu. And mu is a coefficient, and in particular we're going to call it the coefficient of friction. And there's going to be two types of mu. One's going to be for static friction, the other one's going to be for kinetic friction. And so like I said, static friction is going to be a scaling number, whereas kinetic friction is going to be a constant value. So this equation is more accurate for kinetic friction, And I'm going to put a little mu k there for kinetic friction's coefficient. Whereas for static friction, this is going to be not an equal to, but it's going to be a less than or equal to the normal force times mu, because for static friction, again, we can scale up to this number. And so this mu value, mu is this coefficient that deals with basically how rough or sticky a surface is with something else that's sliding upon it, and it's gonna depend upon what those surfaces are. So something like something like carpet would have a very high coefficient of static friction, because I guess you kind of sink into the carpet, whereas the coefficient of kinetic friction would be much lower, because when you start to move that couch across the carpet, it's a lot easier to keep it moving. Something like asphalt would have a very high coefficient of static friction and a high coefficient of kinetic friction, because it's really rough. It'll skin your knees if you fall on it. So let's do a problem here where we have let's kind of take this as an example. I'm just going to redraw it so we can work with it in numbers. So you have an object here, and this object has a certain mass to it, and let's say the mass is like 10 kilograms. And we're on the surface, and I'm going to give you values of static friction and values of kinetic friction. And something unique to this is going to be that static friction is usually going to have a higher number than kinetic friction. I'm not sure of a case where the kinetic friction's coefficient is higher than static friction. It could exist, but I'm just failing to think of one right now. But let's say that the static friction coefficient is going to be 0.6, and usually it's going to be a decimal. It's going to be very rare for static friction to be over 1, but it can be. Kinetic friction, let's say that it's like 0.2. And so we're going to look at this problem here. So we have this box, and we would say, all right, well, the free body diagram, again, of this box is that we have a force gravity down, and we would have probably an equivalent force of normal up. And so the force gravity down is mg, and that's going to be 10 times gg is 10, so it's going to be 100 newtons downwards. Don't need to put the negative because I got the picture. But the normal force here should be 100 newtons as well, because if it's just sitting here, it's not going to be accelerating down or up, so these two forces should directly cancel. Now, in terms of friction, we can say, all right, the friction, at least the static friction, could be less than or equal to the normal force. I'm going to use this equation up here. Normal force is 100, and mu is going to be 0.6. And so what this says is that this is equal to, I guess on this side, this would be 60 newtons. So static friction can be anything from 0 all the way up to 60 newtons. Okay. The kinetic friction, if we were to do that, the force of friction kinetic is going to be equal to our normal force, which is 100 times our coefficient of kinetic friction, which was 0.2. So 0.2, and that's going to be equal to 20. So what we figured out here was that friction, if it's stuck, could be up to 60 newtons, whereas if it was already sliding, friction will drop down to this kinetic value, which is 20 newtons. So right now, there is no need to draw friction because the thing is just sitting there nice and pretty. There's no reason for friction to even exist. But if I applied a force to it, to the right, and let me say that this force is like 50 newtons, and this would be like an applied force, we're just applying a force to the right, what would happen is that friction would start to oppose that. And so friction would point to the left. It's going to try to oppose sliding. That's going to be the good definition for us there. And the frictional force here would be 50 newtons. And the reason I know that is because I look at static friction's amount here, and this is a calculation, but static friction can be up to 60 newtons. And if it was still in the first place, static friction can scale up to 60 newtons. We're only pushing 50 newtons on this thing, so this thing is still still. And so the sum of all forces, let's do this formally. So in the y direction, we have normal force minus gravity, and that should be equal to 0, because the acceleration in the y direction is 0. And so you can see how these two are equal to each other. And the sum of all forces in the x direction is going to be this applied force minus the force of friction. And that should also equal, well, let's say it equals ma, right? Because we don't know if it's going to have an acceleration or not. but the applied force is 50 newtons. And we're going to have to write in what the frictional force here is, knowing that friction can scale up to this number, so up to 60. So 50 is below 60, so friction's just going to scale up. It's going to meet the challenge of keeping this thing still. And so this should result in 0, which means that my MA, the acceleration, is 0. M is going to be 10. Acceleration would be what we're looking for. That's 0 for this to work out. Now, you might ask, all right, well, Mr. K, what happens if the force is like 61? Or what if the force on this thing is like just a bit bigger than the force friction can handle? Well, what we know is that the forces vertically are still there. They're unchanged. mg down, normal force up. 100 down, 100 up. That's all the same. But if we were to apply a force here that was not 50, but let's say it was like, something like 65 newtons to the right, that's our applied force, then friction would still try to oppose that. And so for a picture, friction would still try to oppose that. But in this case, we kind of already know that static friction, in other words, so the friction to hold it still can only be up to 60 newtons. Well, if we push on it and we get 65 newtons, we've broken static friction. So what happens now is we need to go down to kinetic friction, and kinetic friction can only be this number. So kinetic friction is 20 newtons. And so if we look, we've got a small problem. I got the sum of all forces in the x direction. We've got 65 newtons pointing to the right. Our friction is to the left, so I'll put negative, but it's not going to be 60, it's going to be 20 now. It's going to drop down because we've broken static friction. And so if I look at 65 and 20, I'm going to take 20 away from 65. I got 45. 45 is going to be my net force on this object, and that's going to cause some kind of MA, right? Because forces are equal to MA. So here's my overall leftover force. My mass is 10 kilograms, and so my acceleration, if I divide both sides by 10, is 4.5 meters per second squared for the acceleration for this problem. So once you break that static friction, you're going to drop down to a lower frictional value, and then we get some acceleration if we keep on pushing it with that same amount. So you got to be a little bit careful here. So friction, again, can scale to meet your needs as far as static friction goes, but once you're sliding, you pretty much have a constant value for friction. So another problem we can do is just for example, we can say, all right, what if we had like a truck, and this truck, in the bed of the truck, how do I draw a truck? It's kind of boxy. Let's say like that. Let's just draw kind of a, big butt end truck. But anyway, let's put a box in the back of that truck. This is an awful truck. I guess the wheel should be more back here. Hey, look, we just moved the wheel. So you got a truck, and this truck is just sitting in the bed of the truck. So here's this, let's just move the box. It's a 10 kilogram box, right? And so we've got this coefficient, once again, let's use the same kind of surfaces here. So coefficient of static friction is going to be 0.6. The coefficient of kinetic friction equals 0.2 before. And here's this truck. And so you're sitting in the truck, and you are going to push on the gas pedal, and this truck is going to accelerate forwards. And so let's say you push on the gas, and you give this truck an acceleration of like 4 meters per second squared. Okay? Well, if the box is in the back of the truck, that will also have to have an acceleration of 4 meters per second squared. And if we look at the forces that are involved on this object, the thing that's going to accelerate this thing forward, if it's just sitting on the back of the truck, there's no gate here. I guess there is now. But if that box is just sitting in the back of the truck, the thing that's going to try to accelerate this object forward would be friction. Okay, so if we did a free body diagram of this object, got a little less space here, but we still got that 100 newtons down, got that 100 newtons up due to that normal force. But to accelerate the object, we're going to have a force on it to the right. And that force here is going to be friction. And this is a case where friction is actually going to do our speeding up. You know, people say friction will always slow you down. No, friction is actually going to speed you up in this case. And so this is, at the moment, the only force on it. We're not going to utilize the truck's gate yet. We're going to try to see what happens. So if the acceleration of the crate needs to be 4 meters per second squared to just stay on the truck as it accelerates forward, then that means that friction, as far as the sum of all forces go, friction would have to be that force to cause that acceleration. It's the only force that's pointing to the right. So that would equal ma. Okay, that's the thing here. Well, m for the object is 10. A is going to be 4. So we demand a force of 40 newtons from friction in order to accelerate this thing to the right. Well, now the question lies in what can friction be? Can it be 40 newtons? And right now we want that crate to be stuck on there, so it's static friction. It's not sliding friction yet. And so we're going to walk back over to our calculations with the same numbers, and we saw that static friction can be up to 60 newtons. And so right now the requirement for friction is 40 newtons, and so on this free body diagram, you only need 40 newtons to accelerate this crate at a rate of 4 meters per second squared, and so static friction can handle that just fine. But if we said, well, what if the acceleration wasn't 4? What if it was like 8 meters per second squared for the acceleration? Well, in that case, we kind of see that if the acceleration is 8 instead of 4, well, we would require 80 newtons of force in order for this friction to, in order for this box to accelerate forwards. Well, static friction can't handle that. Static friction can only be up to 60. So what's going to happen to this box is that this guy's going to, whoever's in this truck is going to press on the gas, probably pedal to the floor, accelerate you at 8 meters per second squared. The truck's going to move forward. The box is going to try to slide backwards because static friction can't get you that acceleration you need. Kinetic friction is going to take over. Friction is still going to be 20 newtons to the right, but this box will, it's still going to move to the right, but it's going to have a different acceleration on it. And so this box having a force of 20 now equals ma 10a. The acceleration would actually be 2 meters per second squared. So the box is still going to move to the right, but the truck is going to accelerate faster to the right. So really what's going to happen is that if there wasn't a gate here, this box will move to the right, but not as fast as the truck, and it'll fall to the floor. But there's still a force on it to the right. It doesn't just fall straight down. It actually still falls like down. Well, it goes over, then falls down. Okay? So be careful with that. So in this case, if you put the pedal to the metal and just like accelerate it as much as you can, then friction is not enough to hold it still. Static friction is enough. And so kinetic friction will take over. So you're going to have to use the gate here to actually push you forwards. But the first thing that's going to happen is this box is going to want to, well, it's going to seem like it's sliding backwards in the truck, but the whole thing is actually moving to the right. So you got to be a little bit careful with that. I'm going to stop the video. It's a little bit long, 18 minutes already. So hopefully this gave you a pretty decent walkthrough about what friction is. It's just a force that opposes sliding between two surfaces, and that doesn't mean that it's always going to slow you down. We just showed an example of how it could possibly speed you up. But remember that there are two types of friction. One is called static, the other one's called kinetic. Static friction will scale because you can push on a lot of objects and it just won't budge until you push on it hard enough, and when it budges, kinetic friction is what takes over. So we'll end this video here, upload it to YouTube, post it on the canvas. Have a good night.